I can see the pepper on there, and you're gonna put one drop in there, and sure, perfect. And then just watch where you might want to use your fingers to show where your circle starts and stops. Okay.
So
It was a little bit further out from where it is now.
here.
This is the lab we did, lab 5.1. We practiced the dilution, and we're going to see about the size of a molecule. Okay.
It was 0.02.
All right, so I'm going to use these numbers. So the weight of my drops is what were 0.05 grams. So yours is going to be a little different. So if you want the weight of one drop, you just divide that number by 10 or move your decimal place over. So the weight of one drop would be 0.005 grams. So just adding another 0. All right, so diameter of your circle should be about, this one was 8.5 grams. If your weight of your drop is bigger, maybe your circle is bigger. So if it's smaller, maybe your circle's smaller. So about that much. Oh, not grams, sorry. 8.50. You should be able to read to that place. This one was wrong. All right, so the radius of your circle, hopefully you know when you have a circle, the diameter is all the way across. So the radius is going to be from the middle out, right? So you have to divide that number by 2 to get your radius. Okay, so this one would be 4.25 centimeters. Okay, so now we did have done in the past how to measure the weight of a molecule. So you have to know what your molecule is. Hopefully you can see on your page a stearate molecule, which is what we're using. Oh, actually we skipped that the calculation there. So then you take your weight of one drop, that should be the first line there, that's blank. So this one was 0.005 grams. And then if you read in the green part of your book, they said that stearate, which is what you're measuring, is 0.000125, or that percent of how many grams that stearate weighs. So you have to take those two numbers together, which this is why I like to do the calculations together, because you're never going to have to do this part in the lab or on the test. So if you do that, again, hopefully you have a calculator. If you don't have a calculator, you can borrow. You should get a very small number. This one turns out to be 6.25 times 10 to the negative 7th, or 0.00000625. So I don't know what you got on your calculator. I'm not too worried about scientific notation, but you should know that there's one significant digit there. I mean, this is, yeah, just one significant digit, so we're going to keep a few significant digits on there for right now. So really it should be round to 6. All right, so then we have to figure out the mass of the sodium stearate molecule. So again, I would get this information from my periodic table. So a molecule weighs as much as its constituent parts added up. Okay, so a stearate molecule is Na, sodium, plus C18, H25, O2. That's what makes soap soap. Okay, so you have to look on your periodic table. Remember that the bottom numbers are AMUs, but the really important part of it is that's also how many grams per mole it is. And since we're working with grams in the lab, I really care that it's grams per mole. So we're going to use it as grams per mole. So you find sodium on there. There's one sodium molecule or atom. So that's 23.0. So 1 times that. Hopefully you know that one. Then there's 18 carbon. So you got to find carbon on here, and that's 12.0. Got to add that up. There's 25 hydrogens, and that's 1.01. So watch out, that has a couple extra significant digits there. So, and then you have 2 oxygens. So you have 2 times oxygen is 16.0. Okay, so then you have to add those all up. Okay, and when you do that, you get 23.0, you get 226.0, you get, actually it rounds a little bit because there's only 2 there. These are exact numbers, so we don't need to worry about how many significant digits are there. But this one, we should have it. This would be 25 point, maybe her numbers are wrong here. And then this should be 16. Oh, 2 times 16, it should be 32.0. Oh, her numbers are wrong. Okay, so when you add those all up, what do you get? I'm afraid now that her number is wrong. Should be 296.0, because you're rounding to this place when you're adding and subtracting significant digits. Okay, and remember, that's how many grams are in 1 mole. Okay, all right. So we have the weight of a stearate molecule is going to be 296.0 grams per mole. All right, next section. Now, you take your grams of stearate, which is up here in this spot you calculated. Again, mine was 6.25 times 10 to the negative 7th, or put the decimals in, or the zeros in, that's fine. And that's grams of stearate. Now this is the conversion that we're going to be doing a lot of conversions, not necessarily this one, but it's just a conversion. Know how to do a conversion. So I'm going to change, that's of grams of stearate. Okay. I'm going to multiply that by, in 1 mole of stearate, there is 296.0 grams in 1 mole. So the reason I'm doing this is so I can get rid of my grams and go to moles. Why would I want to do that? Because remember my balanced chemical equation? That tells me how many, the big numbers tell me how many moles of something I have. So we're going to be doing a lot of converting grams to moles. Because grams I can weigh in the lab, moles I can use a balanced equation. So it marries those 2 things together. Okay? So, what is a mole? What the whole point of this is for me to figure out how many molecules I have. Remember, a mole is just like when I have a dozen donuts. It's just a number of how many I have. So how many pieces are in a mole? That's Avogadro's number. You will probably have to memorize that for your test. I'm pretty sure you do. I think they give you the AMU one, but I think you have to memorize Avogadro's number. So here I have it written, 6.02 times 10 to the 23. So you need a lot of them to make a mole. A dozen is 12. And a mole is 6.02 times 10 to the 23. A lot. Okay? So it's 6, and then move that decimal place over here so you have 21 more zeros after that. A lot. Okay? When I have a lot of pieces, I have 1 mole. Okay, so that tells me how many molecules I have, because this mole, then this is mole. So that mole cancels out. So that tells me how many molecules. This is molecules in 1 mole, really, is what it is. I don't have that written down there. I just have by how many number. Okay, so that would tell you, with my number, I would get 1.277, that's not 7, times 10 to the 15th molecules of stearate. All right, so that means in 1 drop of soap that yes, question?
How do I figure out the scientific notation again? Like, how do I figure out how many significant digits in those times?
Okay, so when I'm multiplying and dividing scientific digits, this one has 4, this one has 3, this one has 3. My answer can only have 3.
Okay.
Where did you get that number, the first one. I don't know.
This one
Yeah.
was from when I took from this part of the calculations. When I took the weight of my drops, the weight of one drop, and I multiplied it by 0.00125 because that's how much percent of soap, stearate soap is in my water.
Oh.
So
you
your
used
number
it
is
like
going to be a little bit different. This number on
Okay.
yours is going to be different.
that. I knew that. I just didn't know where
Yep.
where it was.
Yep,
Okay.
it's this number right here that's on this lab.
Okay.
Okay, and this number is going to be exactly the same because the grams per mole of stearate should be exactly for you the same as it is for me. The number of molecules in a mole is exactly the same for you as it is for me. So these numbers should match. This one won't. So my number is going to be a little bit different than yours.
So once you have all those numbers, you just multiply through.
Yep. So when you're doing a conversion, you multiply the top numbers, you divide by the bottom numbers. Multiply by the top numbers, divide by, or this, I guess, mole. So that's just multiplied. So multiply, divide by 296, multiply by 602. Okay? All right. Did I lose you? That's why I hate this lab, because it's too many things put together in here. Okay, so ready? I have how many so you wrote down how many molecules you have, right? Okay. Then I need to know the area of your circle. So you measured your circle in centimeters. So my circle radius was 4.25 centimeters. Yours is a little different. So again, your numbers are going to be a little bit different than mine from here. But the process is the same. How do you find the area of a circle? Area is pi r squared. So pi, hopefully you have a pi button. If you don't, it's 3.14 with a lot of other decimals. Okay, so 3.14 times, oh, they have 3.1416, great, times my radius is 4.25 centimeters, and it's squared. Don't forget to square it. So your number here is whatever the radius of your circle was. Okay, so it's your diameter divided by 2, should be calculated up here. Got that? All right, so that's going to be, this one is 56.8 centimeters. This has a lot more, 1/6, it's actually infinite. This one only has 3, so I can only have 3. Okay, so now I take the area of my circle and divide it by the number of molecules. So I should have, mine is 56.8 centimeters squared, because this is squared, divided by my number of molecules was 1.27 times 10 to the 15th molecules. So again, I hope you know how to use your times 10 to the, yes. Get a weird thing.
Okay.
Okay, it is accurate.
Okay.
Okay. All right. So hopefully you know how to do divided by 1 point, whatever your number is, times 10 to the, which might be an EE button, and then put in 15. So again, part of this is how do you use your calculator?
Yeah.
Right.
I don't know
Okay.
what I learned. I don't know what that was for.
Okay. What? So there's you go. This is your conclusion. Please have this in your conclusion. What did you learn? This is how big my molecule is. Is it big?
No.
No.
No, it's very small. Now that seems like such an insignificant thing to learn after all that math, right? We proved that a molecule is really small. Great. The things to remember. Please remember what Avogadro's number is. 6.02 times 10 to the 23rd. That means there's a lot of them to add up to be this many grams. Okay? Know that. And more than that, I don't know. It's small. Say that in your conclusion. Okay,
Yeah.
let's move on. So why? Why do I care? I care to know that molecules are small, atoms are small, yay, fine. The most thing I care about is when I am doing this, I'm going to remember that this bottom number is not just your AMUs, it's how many grams per mole that is. That's so important because we're marrying what I can do in the lab, weighing things in grams, to what I can do in a balanced chemical equation. On page 153, in a chemical equation, let's write one. 2H2O2 turns into 2H2O plus O2. In a balanced chemical equation, this is how many, and there's a 1 here that's not written in, that's how many moles I have. So remember, we learned that you don't lose or gain anything, right? All the matter is there when it started, it's there when I end. You don't lose or gain anything, and this is how many atoms I have. It's how many moles I have. So it marries what I can do in the lab with a conversion to what I can see in a balanced chemical equation. That's why I care about how many grams per mole something is. Yes, learn that an atom is small. You probably knew that before you had chemistry. Okay, so let's do 5A, and hopefully we'll have time. Okay, the decomposition. Oh wait, what was decomposition again? Something's gonna decompose into something else. Okay, break down. So one big thing, break it down into smaller pieces. Okay, I won't rant for you. All right, decomposition of hydrogen peroxide and it turns into water and oxygen described by following chemical equation. Okay, if a chemist begins with, the chemist begins with 2.4 moles of H2O2, how many moles of oxygen are going to be produced? Well, that's interesting. How do I go from this to this? Well, I know that this recipe, because I have a balanced chemical equation, says that for every 2 moles of this, I will end up with 2 moles of hydrogen and 1 mole, it looks like an L, but it's 1 mole of oxygen. So if I start out with more than 2 moles, just like if I 2 1/4 my recipe of chocolate chip cookies, have a good day. We're gonna get more than, if I decompose it into, I'd get a lot more chocolate chips if I doubled the recipe. It's kind of working backwards because I wouldn't decompose a chocolate chip cookie. But if I had more than this, I'm gonna end up with more than this. How much more? So let's figure it out. It's a conversion. So again, I know some people hate to write everything out. Save yourself some time. Write it out so you can see what cancels out, okay? You can convert anything as long as something equals something else. So if I start out with 2.4 moles of this and I want to get to this, I'm going to have to do a conversion such that I know I want to get rid of my moles of H2O2, which is hydrogen peroxide, and I want to go to moles of oxygen. And I can do that because I know that for every 2 moles of this, I get 2 moles of this. Who cares? They're not asking me that. But for every 2 moles of this, I also get 1 mole of this. So for every 2 moles of hydrogen peroxide from the balanced chemical equation, I get 1 mole of oxygen. So I'm doing a conversion that gets rid of my moles of hydrogen peroxide and ends up with my moles of oxygen. You really need to understand this. We're going to do this a ton. So if you don't get this, do less problems. It's from the balanced equation. This sort of equals this. For every one of these, 2 of these, I get 2 of these. For every 2 of these, I get 1 of these. So as long as I have a balanced equation, this will be a true statement. So all I do is I multiply by the top number. I can do that one in my head. And I divide by the bottom number. That one I might use a calculator. Okay, so what's 2.4 times 1 divided by 2? I get 1.2 moles of oxygen. Does that make sense? For every 2, I get 1. Well, I started with more than 2, so I should end up with more than 1, right? So no matter how much I start out with, I can we're gonna even add on to this later on. We'll figure out how much something weighs. They'll say, I have 60 grams of hydrogen peroxide. How many grams of oxygen will I need? Well, then I have to multiply something here, and I have to multiply something here. I'm not quite done. It's gonna be long, and my board gets really small at that point. But this is the beginning of, main thing, make sure you balance an equation. Understand that this many grams is in 1 mole. And once you know what your stoichiometric coefficient is, that is your moles. That's where this gets married to your grams. Okay? So we'll do that step next time, I think. But for right now, let's do one more problem. All right. Hopefully I didn't lose you. This is the second part of it. If a chemist has, now it's going to kind of be backwards, 0.234 moles of C2H6O, how many moles of carbon will he get by decomposing the sample? Oh, they said decomposing. That means I have something big that's going to break down into smaller pieces. So I have, if it's decomposing, I'm going to start out with what they told me, C2H6O. I'm going to break it down. I can't do anything until I have a balanced chemical equation. So I have to break it down into its parts. What's it going to break into? Carbon and hydrogen and oxygen. Okay, do I have it? First of all, is this the right recipe for these? Huh. No, what's wrong?
Something.
Homonuclear diatomics, ding, 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 yay! I even have candy for you if you want. I'll steal it from my kids, but I have it. So, okay, which one is a homonuclear diatomic? Is carbon?
No.
Nope.
Hydrogen.
Is hydrogen?
Yeah.
Yes. Is oxygen? Yes. Am I balanced? No. So, let's balance. CHO, oh look, it's a CHO problem. CHO, how many carbons do I have? How many hydrogens do I have? How many oxygens do I have? There's no number, so it's a 1. How can I make this into, oh, well, let's just check these. Right now I have 1 and 2 and 2. All right, so I have more over here than over here. I have more than over here than over here, so can I have a problem. Where should I start?
With the oxygen.
Yeah, so first of all, I have too much oxygen over here than over here. So I have to start with more oxygen. Okay, so first I have to do what? Make that a 2. So this can be a 2, but that changes this and this. So now what's carbon?
4.
Oh, it's hydrogen. Okay, now I have enough. All right, so now how do I change this carbon to match? Do I put a 4 here?
No.
No, boo, that changes the recipe. I can change it there. How do I change that? That makes that 4. How do I match the hydrogen?
Put a 6 in front of it.
Put a 6 here. Remember, I can't change that now. I can only add a stoichiometric coefficient. And my oxygen is happy. Okay, yay! That's not even close to how we're not done. Now we know we're balanced. And they said, if I have this many moles of this, let me use a different, zip it, go lay down. Sorry about my dog. Okay, so I have 0.234 moles of this. Did they ask about carbon? No, they said how many, well actually they did, so that's what we're looking for. I don't care about that, I don't care about that, they didn't ask me. I can figure it out, but they didn't ask me, so I'm gonna forget it. So, in the balanced equation, for every 2 moles of this, I get 4 moles of this, and 6 moles of this, and 1 mole of this. So as soon as I know the balanced equation, then once I know one of any of them, I can figure out all of them. So we're going to, I think my kids are home, that's why he's freaking out. So we're going to take what we know, 0, it's not a 0, 0.234 moles, and again I would label it C2H6, going down. I'm going to multiply it so that I get rid of my moles of C2H6O, and I want to go to moles of carbon. So how many moles of carbon for every mole of this? I get that from these numbers here. So for every 4 moles of carbon, I need 2 moles of C2H6O. So these numbers is just a ratio from my stoichiometric coefficients once I've balanced. All right, so now my moles of C2H6O gets canceled, my moles of C2H6 gets canceled, and I'm left with how many moles of carbon I will end up with. So when that much breaks down, how much do I get? Well, I take that number times the top number divided by the bottom number. In this case, I could just multiply it by 2. So you'd stick it in your calculator, and you would get 0.486 moles of carbon. And I have 2 significant digits there. These are exact, so they don't count. So I get 3 significant digits. 3 significants there, 3 significant digits there. And it's labeled. The whole point of this was to figure out how many moles of carbon. Please tell me how many moles of carbon I have. Okay? Sorry that the lab measurement calculations went long. We will do more of this, guarantee you. If you are completely confused, please, 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 I beg of you, do all of your review questions and practice problems for sure, because this is foundational. We're just going to add on to this. It's just going to get to be a longer problem, but this is exactly what it is. So make sure you know decomposition, formation, and combustion. Remember to add oxygen. Remember, oxygen is a homonuclear diatomic. Make sure you balance your chemical equations. Okay? So next time you're going to give me a lab, which is mostly done, and you're going to give me a test. Okay? And if you have any questions, email me, call me. Okay?